So one more topic in the general area of conjugate addition reactions, and that is when the nucleophile, so in the last video, we looked at an amine as a nucleophile, we looked at hydride as a nucleophile, but what about when the nucleophile is an enolate? Well, when the enolate is a nucleophile, conjugate addition is going to be the preferred product, and this product is called a Michael addition. Michael was actually the last name of the person who discovered this reaction. So an example is shown on the screen. So in this case, we have the enolate of acetone, a simple ketone, being added to an alpha beta unsaturated ketone, and the new carbon-carbon bond that is formed during this reaction is indicated in red. What you should also note is that the product is a 1,5-dicarbonyl compound. Okay, so remember, the enolate fragment, once it uses its electrons to form a new carbon-carbon bond, that reforms a carbonyl group. And then in the alpha beta unsaturated carbonyl fragment, if we are doing a conjugate addition, the carbonyl group is going to be maintained in that fragment also. So we end up with two of those stable CO bonds in the final product. Okay, so let's look at the detailed mechanism of this reaction. And I'm assuming by this point in watching these lectures that you know how to make an enolate, and I don't have to show that explicitly. So once you have the enolate, it's going to add to the carbonyl, and this particular step requires 4 arrows in one step. We've never seen 4 arrows in one step before. That is, of course, assuming that we use the major resonance form of both the starting enolate and the final enolate for this step, in which you have a CC pi bond and the negative charge on the oxygen. Okay, so from left to right, arrow number 1, the minus charge on the oxygen forms the CO pi bond. Arrow number 2, the electrons in the CC pi bond form the new CC sigma bond shown in red. Arrow number 3, the CC pi bond shifts over, and then arrow number 4, the CO pi bond breaks, putting the electrons onto the oxygen. Okay, so as I already alluded to, the product of this step is an enolate. So it is no more or less stable than the starting material for this step is. And given that we are under basic conditions, in that we have an enolate starting the reaction and no proton source is present while this step is taking place on all molecules, this enolate is going to hang around until the workup. Okay, and then there needs to be an acidic workup, as is true for many of these reactions. And during the acidic workup, the enolate is protonated to give the neutral product. And again, the way we draw it from this resonance structure is we just have the minus charge on the oxygen coming down to form the CO pi bond, and then finally the electrons that were in the CC pi bond forming the new CH sigma bond to the alpha carbon. Okay, so that's a Michael addition, the addition of an enolate, and this is the third example of a carbonyl condensation reaction. So the aldol, Claisen, and Michael are the big 3 of carbonyl condensation reactions because they initially start with 2 carbonyl compounds, bring them together, forming a new carbon-carbon bond. And as we said at the very beginning of this unit, the formation of carbon-carbon bonds is an important step in increasing structural complexity in organic molecules. And I want to leave you with a very nice example of how we can craft a molecule that is somewhat complex out of what looks like very simple starting materials. And that is a reaction that is called the Robinson annulation. So you may recall that a 1,5-dicarbonyl compound, which is the product of a Michael addition, as we just saw in the last slide, is something you've actually seen before in a previous video in this unit. A 1,5-dicarbonyl compound is the starting material for an intramolecular aldol condensation that is used to form a 6-membered ring. So if we put these two reactions together back to back, first we do a Michael and then we do an intramolecular aldol, it is called a Robinson annulation. Okay, so first look at the example and then we'll talk about why it's called what it is. Okay, so we are taking ultimately two ketones. And the product we're eventually going to get out has the 6-membered ring on the bottom right. So the reason that this is called an annulation as opposed to a cyclization is because annulations are reactions that form a ring from two linear fragments through the formation of two bonds in the ring. So in this case, one of the ketones, the acetone, is the atoms labeled 5, 6, and 7 in the final product. The other ketone has the atoms labeled 1, 2, 3, and 4. And the two new bonds that you have formed through this annulation process is the double bond, the carbon-carbon double bond between C1 and C6, indicated in green, and also the carbon-carbon single bond between C4 and C5, shown in red. Okay, so let me walk you through this in just a little bit more detail. So one of our starting materials is going to be acetone. It could be something more complex, but I just like to use acetone as a simple case so you get to see what's really going on in this reaction and not get lost in the spinach. So we've already seen how you can use LDA as a base and deprotonate acetone completely and quantitatively and irreversibly to give its enolate. So once we have the enolate of acetone, we're now going to add it to the alpha beta unsaturated carbonyl compound, the alpha beta unsaturated ketone that we looked at on the previous slide. I want to keep this as simple as possible, so we're keeping the substituents the same. And that's going to give us the same 1,5-dicarbonyl compound that we saw on the previous slide. Now, I have this chain numbered differently. I have a carbonyl at carbon 2 and a carbon 6. But it is called 1,5 because that's just the relationship between how many atoms apart the two carbonyl groups are. So as you can see in the Michael reaction, the first reaction, we have formed, so carbon 5 is the nucleophile, carbon 4 is the electrophile, and we have formed the new carbon-carbon bond indicated in red between carbon 4 and carbon 5. Now, when you take this and heat it up with sodium hydroxide, the beauty of this molecule is that it is symmetric. So it doesn't matter which end I deprotonate. But what's going to happen to get you to the 6-membered ring is I have to deprotonate either carbon 1 or carbon 7. They are equivalent. For the sake of argument, I'm just going to say that we are deprotonating carbon 1. And then that will come around and add to the ketone at carbon 6. It will initially give you the beta hydroxy ketone with an OH group at carbon 6, but then the aldol will undergo dehydration to form a double bond between carbon 1 and carbon 6, giving you the alpha beta unsaturated ketone as the final product. And remember from the discussion of the intramolecular aldol reaction that in this case, if you were to deprotonate carbon-3, that would be the thermodynamic enolate, but carbon-3 would never add to carbon-6 because that would form a 4-membered ring rather than a 6-membered ring. Okay, so that's the Robinson annulation for you, and the reason it's called the Robinson annulation is because its discoverer was the British chemist Sir Robert Robinson. All right, so that now brings us to the end of this unit on carbon-carbon bond-forming reactions, carbonyl condensations, enols, enolates, aldol, Clays, and Michael, and we've seen a few neat applications in there. As we move forward now, we now have a toolbox of reactions that are big enough for us to start to consider the concept of multi-step organic synthesis. This is an introduction to multi-step organic synthesis, but we're going to go even further with it as we move into the next unit.